Here to start chapter 5, we're going to start looking at trig identities. And on this sheet or on this page, you'll have the fundamental trig identities that you're basically going to be asked to know / memorize. I hate to use the word memorize, but you do need to know these kind of inside out. Some of them we have experience with, others will be new. So looking down through here, our reciprocal identities, those should make perfect sense from our previous work in chapters 1, 2, and 3. We know that sine and cosecant are reciprocal, so cosecant equals 1 over sine, or sine equals 1 over cosecant. Cosine and secant are reciprocals, and tangent and cotangent are reciprocals. So 1 through 6 are reciprocal identities. They're equal to each other, so we can replace one with the other. Product identities, we know if we have reciprocals in math, the reciprocal 1/3 is 3, and if I multiply reciprocals together, I get a product of 1. So it follows if I multiply in trig, sine times its reciprocal of cosecant will give me a product of 1, cosine times secant will be a product of 1, and tangent times cotangent will be a product of 1. Our ratio identities here, back when we talked about our unit circle, we said sine was our y value and cosine was our x value, and we know tangent is y over x, so it follows tangent is sine over cosine. Same thing with cotangent is x over y, or cotangent is cosine over sine. Down here at the bottom, where we might have to spend a little bit of time looking at our Pythagorean identities, we did look at cosine squared plus sine squared a little bit in chapter 3. As our first Pythagorean identity, if we were to take that identity and subtract one of those values from each side, so let's say I want to subtract the sine squared from both sides, that would give me my alternate form of cosine squared equals 1 minus sine squared. Same thing would apply if I subtract cosine squared from both sides. I get sine squared equals 1 minus cosine squared, and so on. The next identity, number 13 here, 1 plus tangent squared equals secant squared. Alternate forms over here on this side as well. If I subtract tangent squared, I get 1 equals secant squared minus tangent squared, or tangent squared equals secant squared minus 1. And our last Pythagorean identity is cosecant squared plus 1 equals cosecant squared, and you can read through the alternate forms as well. Bottom line is this page you probably need to know inside out. I am going to add 3 to this, or actually 6 to this, the opposite angle identities. Cosine of negative x equals the cosine of x. Cosine and secant are reciprocal, so they follow the same values here. Secant of negative x equals the secant of x. Our second set, sine of negative x. Let's try that again. Forgot my negative sign. So sine of negative x equals negative sine of x. We'll just move the negative sign out in front. So the cosecant of negative x equals negative cosecant x. And then our last two, the tangent of negative x is the negative tangent of x, and the cotangent of negative x equals negative cotangent x. So it's simply noting that cosine and secant are the ones where the negative sign can essentially disappear. With the other 4, the negative sign can move from the angle to out in front of the function. From here, we're simply going to do some work to prove identities. But we'll run through a quick warm-up here first. It says if tangent of s equals negative 5/3 and s is in quadrant 2, find each functional value. So maybe I should not say s. These are in terms of theta, so let's change these to be theta instead of s. So we'll put theta over here instead of s. Over here, anytime we want to find secant, sine, or cotangent, it's probably easiest to find x, y, and r. From tangent, we know that y is 3 and y is 5 and x is 3. And because we're in quadrant 2, we have a negative fraction here. X is negative in quadrant 2. If we did negative 3 squared plus 5 squared to be r squared, we'd find r to be the square root of 34. Secant is r over x, or in this case the square root of 34 over negative 3. Sine is y over r, which is 5 over the square root of 34. If we rationalize the denominator, we get 5 times the square root of 34 over 34. A little bit of work here. Cotangent of negative theta, we just said was the negative cotangent of theta. So I'll leave my negative sign. Cotangent is reciprocal of tangent, so if tangent is negative 5/3, then cotangent is negative 3/5. I have a negative negative, so my cotangent of negative theta is a positive 3/5. I'm going to skip over the second one, A and B, because that's and C and D, but those are pretty much identical, and get into actually some identities here. Sine times cotangent is going to reduce down to cosine. No one set way to start any of these problems, but one suggestion I can give you is to start in terms of sines and cosines. So in other words, I'm going to change or leave the sign as it is. I'm going to go back to my identity sheet and try and change cotangent to be in terms of sines and cosines. So I go back here just a little bit, and I find that cotangent is cosine over sine. So I'm going to make that substitution and say that cotangent is cosine over sine. And when I'm multiplying, I can always cross cancel before I multiply, so I can cancel the sines, and I have 1 times cosine to be cosine over 1 times 1, which is 1, and cosine over 1 is just cosine. So that's kind of the basic idea here, is we're going to change one statement to become the other by using those identities and also by using our algebra skills here. In this case, we were cross-canceling numerator and denominator. As I mentioned when we started the first one, there's no one set way to start each problem. Here we change the sines and cosines. Here we have two binomials that we're going to go ahead and multiply together by using the FOIL process. So if I FOIL, first terms, 1 times 1 is 1. Outer terms, 1 times negative cosine is minus 1 cosine. Inner terms, cosine times 1 is plus 1 cosine. And last terms, cosine times negative cosine is minus cosine squared. So there's our FOIL process. There is a shortcut version of that if you recognize that these two terms have the same two terms, 1 in cosine, 1 in cosine, but have opposite operations in between. Those two terms are called conjugates. And we multiply conjugates in the FOIL process. As I said, we can shortcut that because the outer and the inner cancel each other out, so we can just do first and last. And you can see that here. I have a negative cosine and a positive cosine. They cancel out to be 1 minus cosine squared. These become 0 right here in the middle. And then back to our identity sheet, as we look through here, 1 minus cosine squared, you see equals sine squared, which is what we were trying to get to. So that equals sine squared. We have changed this product over to sine squared. Again, that's kind of our process for these identities. Moving right along here, our next one here at the top of the page says 1 plus tangent squared over tangent squared times 1 plus cotangent squared is going to reduce all the way down to 1. Now what you'll find, and maybe I'll illustrate this here, but there are more than one way to go through some of these problems. So 1 plus tangent squared, backtracking to our identities, 1 plus tangent squared down here is secant squared. So we'll make that substitution. Also noting on our denominator, cotangent squared plus 1 is cosecant squared, so we'll make those two substitutions into my identity up here. In place of the 1 plus tangent squared, I'm going to put secant squared. And in place of the 1 plus cotangent squared, I'm going to put cosecant squared. And that should hopefully seem like a fairly logical first step, because that does get rid of some of my plus signs and starts to get us down to fewer terms to deal with. From here, secant squared is 1 over cosine. So if secant is 1 over cosine, so secant squared then is 1 over cosine squared. Tangent is sine over cosine, so tangent squared is sine squared over cosine squared. And cosecant squared, or cosecant is 1 over sine, so cosecant squared is 1 over sine squared. So I change the sines and cosines. My 1 over cosine squared is going to stay here for right now. My denominator, I have two fractions I'm multiplying together. The sine squareds will cancel between numerator and denominator, and I'm left with 1 over cosine squared. I'm dividing with fractions, which means I have 1 over cosine squared multiplied by its reciprocal of cosine squared over 1. And you can see more canceling going on to 1s and 1s. We've simplified it all the way down to 1. Okay, so as I mentioned, there's more than one way for some of these problems. So up above here, I'm going to try that same problem again. I'm going to leave the 1 plus tangent squared as it is. I'm going to distribute in my denominator to remove the parentheses. So tangent squared times 1 is tangent squared, and tangent squared times cotangent squared is just that, tangent squared times cotangent squared. From our identities, backtracking 2 pages, notice that tangent times cotangent equals 1, so tangent squared excuse me, times cotangent squared would equal 1 squared. Well, 1 squared is still 1. So I'm going to replace this with 1 plus tangent squared over tangent squared plus, and I just said that tangent squared times cotangent squared is 1 squared or 1. Notice now I have something divided by itself or 1. Doesn't matter what order I add terms together in, and they still add to be the same value. So 1 plus tangent squared is the same thing as tangent squared plus 1. I'm dividing something by itself, so my quotient is 1. So as you mentioned, I mentioned 2 different ways to solve that problem, and that will be the case in a lot of the problems that we work with. Moving on, secant minus cosine is going to become tangent times sine. I don't know where else to start, so I'm going to change secant to 1 over cosine and leave cosine as it is, but for visual effect I'm going to put it over 1. Noting that I have 2 terms joined by subtraction here, and over here I have a single product, so I want to try and combine these 2 terms into 1, which means I want to find a common denominator. And maybe I'll do this in 2 parts here. So my common denominator between these 2 fractions is cosine. To move from cosine to cosine, I don't need to do anything but multiply by 1, so this numerator will stay the same. But to move from 1 to cosine, I have to multiply by cosine, which means I have to multiply the top by cosine as well, and cosine times cosine is cosine squared. I can now write that as a single fraction as 1 minus cosine squared all over my common denominator of cosine. Common denominators are a common procedure here, so hopefully that process made sense. Think of that in terms of numbers of 1/3 plus 1/4. 1/4. My common denominator for each of those would be 12. So to move from 3 to 12, I have to multiply by 4. So I multiply the top by 4 and get 4 12s. To move from 3 to 12, I have to multiply by 3. So multiply the top by 3, and I wound up with 4 plus 3 over 12. This is just a situation because of numbers, we can get to 7 12. So the same idea with our expressions here, our variables. Obviously we can't combine because of the numbers. Okay, so to continue on here, 1 minus cosine squared is a Pythagorean identity of sine squared. So we'll make that substitution. And then all it's left to do is manipulate that to become what we want. If we recognize on that front sheet, tangent is sine over cosine. So I'm going to rewrite my sine squared as sine times sine and put one of those over cosine and one of those over 1. Just a different form. Sine times sine is still sine squared. Cosine times 1 is still cosine, but just allows me to get to the form that I want because sine over cosine is my tangent and sine over 1 is sine. Okay, so we applied some algebra techniques along with knowing our identities to go ahead and simplify there. Let's go again here. 1 minus sine to the 4th over cosine squared is going to reduce down to 1 plus sine squared. One of our other common ideas here is to factor what can be factored. So 1 minus sine to the 4th represents the difference of 2 squares. An algebra parallel, if I have x squared minus 4 and I told you to factor that, I hope most of us would recognize that to be x minus 2 times x plus 2. So I'm going to apply that idea to 1 minus sine to the 4th and factor that to be 1 minus sine squared and 1 plus sine squared. Okay, factoring the difference of 2 squares. At the same time I do that, cosine squared is not part of my final answer, so I want to change cosine squared to something. Its Pythagorean identity is 1 minus sine squared. So one set of factoring and one identity here. Once we have that, between numerator and denominator, the 1 minus sine squareds are like factors. They cancel each other out, and we're left with 1 plus sine squared as our identity. Let's try one more on this page. Cosine plus tangent times sine is going to reduce to secant. So cosine, I'll change tangent to be sine over cosine and leave the sine as it is. So changing it into sines and cosines. I'll put this over 1, maybe this over 1 for visual effect as well. But cosine then over 1. I'm going to go ahead and do my order of operations. I'm going to multiply this together first. So sine squared over cosine. Have two fractions there. I want to combine to be a single term. So I'm going to find a common denominator. Cosine times 1 is cosine, which means my first numerator has to be multiplied by cosine, which gets me cosine squared. My second numerator is going to stay the same as sine squared. If we continue on, cosine squared plus sine squared is a Pythagorean identity of 1. I have 1 over cosine, and 1 over cosine is secant. So we have proved another identity.